Yeah, good morning.
Good morning.
So there will be 2 lectures on vibrations and how one can calculate them using ab initio techniques. So that's basically the idea of these 2 lectures I'm going to give you today and the next week. And if we're going to talk about vibrations, then we have to start from the separation of electrons and nuclei. So this is what we call adiabatic approximation. So so you must have heard about this, and maybe you know this already, but I really need to start from that point because this is an essential conceptual point. We have to understand this one. First of all, what is the Hamiltonian of the whole system? If we have a condensed matter system or a molecule, it consists of nuclei and electrons, and therefore, if we would like to solve a Schrdinger equation for that system, we need to consider the full Hamiltonian. And then Hamiltonian consists of the electronic part, nuclear part, and interaction between the two. Yeah, so this is our Schrdinger equation. And in the Schrdinger equation, this capital R corresponds to all nuclear coordinates and little x to all electronic coordinates. So the wave function would depend on both variables. So these are 2 types of particles, electrons and nuclei. Nuclei are bosonic type particles, electrons are fermionic-like particles. So you will have a hybrid wave function, and the Hamiltonian depends, of course, on both. So here you see an explicit expression for the particular terms in the Hamiltonian. Electronic Hamiltonian contains kinetic energy of the electrons, electron-electron interaction. Nuclear Hamiltonian contains also a kinetic energy for nuclei and interaction between nuclei. And the electron-nuclear interaction is just a Coulomb attraction between the 2 types of particles. Right. So this is a rather complicated problem. One argument which we can put forward is that nuclei are much heavier than electrons. And therefore, in the first approximation, one can consider nuclei frozen. If the nuclei are frozen, we can forget about the kinetic energy of the nuclei and consider simply electronic problem. When nuclei are frozen, positioned at some points described by this vector variable r, it's a variable which contains all the coordinates of all the nuclei in our system. Yeah, so it's not just one variable, it's not a single variable, it's basically a vector. Yeah. And then solve the Schrdinger equation just for the electrons. So that Schrdinger equation contains the same Hamiltonian as before, only the kinetic energy of nuclei is missing. Yeah, and nuclear positions, they come as a parameter. So now the wave function still depends on the nuclear positions, but it depends on them as a parameter. If we change nuclear positions, we have just another electronic wave function and another electronic energy. Electronic energy here is not just electronic energy, it contains nuclear-nuclear interaction, which is a constant for the given positions of the nuclei, but it's convenient to include it in that energy because then we can interpret this energy, not just an electronic energy, but the energy of the whole system when nuclei are fixed. And therefore, if we change positions of the nuclei, that energy would change, and that would be the change of the total energy of the system in that kind of approximation when nuclei are treated as frozen. The advantage of that approach, when we start from frozen nuclei, is that for each positions of the nuclei, we have a complete set of the wave functions for the electrons. And therefore, if we return back to our original problem of solving this complete system for quantum mechanically for both nuclei and electrons, we can actually expand the total wave function in terms of these wave functions we found from this auxiliary problem. And the coefficients would depend on the capital R, on the positions of the nuclei. So if you apply this approach in practice, then which is exact, because we just expand the total wave function with respect to some particular complete set of functions. If you apply this approach, you will have a set of equations, differential equations of the second order, with respect to electrons, this one, and also with respect to the nuclei, which will be manifested by equations for these chi functions, depending on the R. And if you do this, you would go beyond the adiabatic approximation. This would correspond to non-adiabatic approach. We're not going to consider this here. I'll just concentrate on the adiabatic picture, in which, in that sum here, we only take account of a single state of the electron. So that index C would take up only one value corresponding, for example, to the ground state of the electronic system. Okay, so this C is a set of quantum numbers associated with this Schrdinger equation. It would take just one value. If this is the case, then the wave function of the whole system is approximately given by a product of this function, which would correspond to the coefficients of this infinite expansion, otherwise, if we have taken into account all the terms. But as we have taken just one term, this would be a function, yes, depending on the nuclear positions, and the electronic wave function also depending on the nuclear positions as a parameter. If you now take this function and substitute it into the Schrödinger equation here, you can derive an equation for that function, for this chi function. This is what you get. So that term, which appears in place of the potential energy. So this equation looks like a Schrödinger equation, right? Which depends only on the nuclear position. So we can interpret it as a Schrödinger equation for the nuclei. And that term here, which serves as a potential energy of that nuclei, consists of this potential, of this total energy of the whole system for fixed nuclei plus some additional terms, which are not very large. So basically, if we neglect this term, which is not very large as compared to this one, we can interpret this equation as a Schrödinger equation for nuclei, which move in the energy which we obtain from solving the electronic problem. And this is quite convenient, because if you think about it, we would expect that that energy would have minima. So if I imagine some coordinates of my system, say x, y, and some z, many coordinates of all atoms of my system, and vertical axis would be that energy u, you would imagine that there will be some minima at some positions of the nuclei, yes, where atoms would like to stay, and at other positions you have maxima, saddle points, and this would be points associated with arrangements of atoms which are not mechanically stable, and only this minima in this function with respect to this capital R would correspond to stable positions of the system. The lower the value of that in that minima, the more stable that position would be, and the lowest of all would give us the ground state of the system. Others would correspond to metastable states, where the system is still stable, but has a great chance, given enough thermal energy, for instance, to escape and arrive at another minimum. Okay, so so this is the picture of so far we've got adiabatic approximation, in which electrons are described independently of nuclei movement. In fact, for each positions of the nuclei, we determine the electronic wave function, this psi, And then we determine these energies as eigenvalues of this electronic problem. And once we've got those, we try to solve the equation for the other factor of the total wave function, which is interpreted as the nuclear wave function. When is this approximation valid? It is valid when you consider this potential energy. So this quantity is called potential energy surface, and it is governed by this index C, which is a set of quantum numbers for the electronic subsystem. And of course, when you solve this equation, you not only get the ground state, the lowest possible energy for the given nuclear position, you get also excited states. And if we now plot those, so this would be the ground state as a function of this capital R. This is obviously just a plot to give an idea, because this R is a vector. I can't possibly plot this it as a vector here, so I use it as just single coordinate. But this would be other states. So if these other excited states are well separated from the ground state, so these energies are much larger than the energies which we will fill up here by considering phonons, which is a solution of that equation, then this adiabatic approximation would be valid. In other words, in simple terms, that means that adiabatic approximation would be valid if we need to create many phonons in the system by exciting that system to reach the nearest excited state or states. Yeah, if we require very many phonons, and that would require high temperatures, for instance, if we require many phonons to reach this excited state, then this ground state picture, ignoring the excited state, would be valid, and therefore the adiabatic approximation would also be valid. Okay. So by solving the electronic problem, we get the wave functions. We also get this adiabatic potential U. What can we learn from this adiabatic potential? As I already mentioned, if we plot this adiabatic potential as a function of atomic positions R, capital R, then it may have many minima. Yeah, the lowest minimum would be the ground state of the system where it would spend most of its time, but there could also be some metastable states with the lower energy, which are also legitimate states of the system, because the system there is stable, provided that the barrier to overcome in order to escape from that state is non-zero. Yeah, then this system would be, that state would be stable. Of course, the higher the temperature, the greater chance of escaping from that state into the ground state. But in thermodynamic equilibrium, you would have a balance associated with the canonical distribution, when states with the lowest energy would be most probable, but there will be a certain chance for the other states to exist as well. So by studying this potential energy surface as a function of the nuclear positions, we can learn about the structure of our system in the space of nuclear arrangements, where the minima are, how deep they are, how many of them are there. Also, we can look at the barriers separating different minima. Yeah, and these barriers are quite important. For example, in order to get from the ground state to that excited state, we need to overcome that barrier. But if we go in the opposite direction, it will be a smaller barrier to overcome. And these energy barriers are quite important because they determine the rates for the system to undergo a transition between different minima. So by studying the potential energy surface, we get not only the positions, capital R, where atoms are for the ground state and various metastable states, we also we also have an information about the energy barriers which are required to overcome when going from one state to the other. And that may help us to study dynamics of the system in real time. And for example, kinetic Monte Carlo methods, which I'm not going to consider here, require knowledge of these transition rates, and therefore require knowledge of these energy barriers. So you can see that potential energy surface of electrons in the fixed positions of the nuclei is a very, very important quantity, this potential energy surface. But what also does it give us? It gives us atomic vibrations, because when this term is here, this would be a Schrödinger equation for the nuclei wave function. And therefore, by studying the curvature of this potential energy surface around different equilibrium positions of the nuclei, around here or around here, would give us a way to determine this nuclear wave function and therefore study vibrations. And vibrations play important role in many areas of condensed matter. They determine thermal properties, transition rates. Again, I will show you this, and determine stability of the system at different positions. So, so we need to solve this Schrödinger equation for the nuclei wave function, where the role of the potential energy is played by this eigenvalue of the electronic only problem. And you see, I remove this Xi index here because I consider just the ground state of the electronic system. Of course, this consideration applies to excited state as well, provided these excited states are well separated as well from other excited state, which is not very often the case, actually. Okay. And by the way, another thing I would like to note is that if the system is in the ground state, being in the ground state and considering vibrations of that system here around the ground state may be quite legitimate in the adiabatic approximation. However, if you have a metastable state here somewhere, and you would like to consider vibrations around that point, this excited state may come very close to it. So you have to be really careful in applying the adiabatic approximation. You have to investigate where for the same nuclear positions, excited states of the full electronic problem are to be sure that that adiabatic approximation is valid. So in order to solve this equation, what we can do, we can expand this potential energy term in terms of atomic displacements. So if in the minimum atoms are at positions R0, here capital A means atom, and alpha means XYZ, the component, Cartesian component of the atomic position. So these atomic positions are at equilibrium, and this is a general position somewhere here, and the difference between this would give us a displacement. And we assume that at low temperatures, and we only consider sufficiently low temperatures, because at high temperatures you have a chance of the adiabatic approximation to be broken. So at low temperatures, okay, I will mention that at temperatures below the Debye temperature, but I'm not going to go into details for that. So what you do, you expand this potential energy in the Taylor series with respect to these displacements. If the temperature is not very large, then these displacements are assumed to be rather small. Atoms would display quite a little around that the equilibrium. Just use a classical intuition for that. If you have a potential energy well and your temperature is not very large, atoms would oscillate just with a small amplitude, and therefore their displacement from the equilibrium positions would not be very large, and that justifies this kind of expansion of the potential energy. Because we're using expansion around the equilibrium position, when the first derivative of the energy with respect to atomic positions is 0, then this first order term will be 0 as well. Yeah, because the Taylor coefficient here is just that derivative. Therefore, because this term is 0, the first non-zero term will be quadratic in the atomic displacements. And here you will have a second order derivative with of the potential energy surface E with respect to the atomic positions, calculated again at equilibrium, which is designated by this 0 here. And that object for all atoms and all their Cartesian coordinates forms a square matrix, Cartesian matrix of the second derivatives, which is in this business of vibrations called force constant matrix. So if we just limit ourselves to the very first non-zero term in the expansion of the total energy of the total electronic energy with respect to atomic displacements, then this harmonic term, quadratic in atomic displacement, would be the first one, and we would just leave that term and remove all the cubic, fourth order terms, etc., which are called anharmonic. Of course, these are less important. The first non-zero term would be more important. Then we arrive at the so-called harmonic approximation. So if we are within the harmonic approximation, then the potential energy of the system, which enters this Schrödinger equation for the nuclear wave function, would be just a square polynomial with respect to atomic displacements without linear terms. Yeah, that's the important point for our discussion right now. Right, in the classical picture, what does it mean in the classical picture? In the classical picture, that means that this potential energy surface is a parabola in a multidimensional space, or paraboloid in a multidimensional space of atomic vibration, of atomic displacements. And in the classical picture, that would mean that if you allow these atoms to move, they would oscillate within that potential energy well, which is harmonic. Can you hear me well? My internet connection, it says not really great. I'm just checking.
Yeah, the sound sounded a little bit weird, the last sentence. But... Yeah, but now it's fine.
Now it's okay. Huh?
Yeah.
All right. Because it might vary there. So what I was saying, that in the classical picture, you would imagine that the system would oscillate in that potential energy well as a harmonic oscillator, yeah, but it will be a dimensional harmonic oscillator, of course. We will come to this. In the quantum mechanical picture, it will be slightly different. I already mentioned that briefly, because in the quantum mechanical picture, we have to solve this Schrödinger equation, and then we will have a set of eigenvalues. And again, you can imagine, since we have kind of a harmonic potential, but with many degrees of freedom, but you know it from a single harmonic oscillator. In a single harmonic oscillator, I have energies En, which are h omega n plus 1/2, with this n 0, 1, 2, all integers. So we see that for a single harmonic oscillator, excitation energies for the vibrations are equidistant with the energy h omega, where the omega is vibrational frequency. In the multidimensional harmonic oscillator, this is what we have here, multidimensional, because we have many degrees of freedom, many atoms, many displacements. We will have slightly more complex picture, but essentially it is the same. We have vibrational frequencies, and we can excite these different vibrations up to any order we like. And that would mean considering excitation energies for our multidimensional harmonic oscillators, and this would fill up this potential energy well. And as I return back to what I said at the beginning. So if you have very high excitations of these phonons, you may reach the second potential energy surface, and that would break down the adiabatic picture. So we assume that we don't have that many phonons, and that corresponds to not very high temperature. Again, we will look at this later on, in order to remain within the adiabatic picture. But basically, this is the idea. In the classical picture, you have an oscillation within the potential well. In the quantum picture, you have these excitations. As the higher the temperature, the more excitations of the phonons you have filling up this potential well. And the total energy would become the total energy of the electronic system in the minimum, plus a certain vibrational energy of your harmonic oscillators. In the classical picture, you have the energy in the minimum plus the classical vibrational energy of the oscillators. So these two pictures are very, very similar in a sense. Okay, so what we're going to do now, we'll try to consider a classical picture entirely, and we will try to solve classically atomic vibrations. Of course, you know how to do it for a single harmonic oscillator. So what I will demonstrate to you is how one can do it for a multidimensional problem when your potential energy is a multidimensional square polynomial of atomic displacements. But first, let's make a few notes about the force constant matrix, which we have here in the expansion of the potential energy of our system with respect to atomic displacements. And here I use simplified notations. Remember, before we had capital A and alpha. A stands for a particular atom and alpha stands for Cartesian components. Now we just use a single index. It's much easier because it's a quadratic form. Of course, that matrix is symmetric, and also it comes from the fact that that matrix is a Hessian, and you know from mathematics that second order derivative is symmetric with respect to the order in which one and the second derivative are taken. Yeah, so I'm referring to this formula here. This second derivative forms a symmetric matrix. But this is a general statement. There are also some particular statements one can make about that matrix. One is that the following equation is satisfied for any system. It could be a molecule, it could be a crystal. Why is this so? If we take our system, we assume that the energy of our system as a function of atomic displacement is described by that formula. Okay, and we are free to choose any displacement we like, would still be within that formula. Let's choose all displacement being the same. Of course, if all displacements are the same, the whole system just will be shifted. And you would expect there will be no change of energy, right? So that can be reformulated in the following way. If we would like to calculate a force acting on an atom due to some displacement, what we need to do, we need to calculate minus derivative of that energy with respect to some atomic displacement. That derivative would obviously give us minus sum over so if I, let me write it maybe. If I differentiate energy with respect to atomic displacement J with the minus sign, that will give me a force acting on the atom, on the degree of freedom J. And if I now differentiate that expression, what I will get minus sum over I, phi J I U I. Yeah, so that would be the force. All right, that would be the force. So the force acting on the atom A, capital A, direction alpha, is given by the derivative. It's given by this a single sum. Yeah, and now if we remember what our assumption was, all displacements are the same, so we can take them out. Let's call them V. They form vector V. We take them out. What we're left with, this, which sums over all atoms, arbitrary alpha and alpha prime. And because that force must be equal to 0, which would correspond to the fact that the energy does not change as we shift the whole system, we obtain that expression. for the force constant matrix. So force constant matrix must satisfy this condition. There's also another condition you can imagine, which I am not putting here on the slide, but if you rotate the whole system by a certain vector, all atoms would be rotated appropriately if we choose a rotational axis and the angle of the rotation. And again, some atoms will move more, some atoms will move less, depending on where they are with respect to the rotational axis, okay? But at the same time, the energy should not change, must not change. Therefore, there will be another condition one has to impose. One has to impose on this matrix with respect to due to rotations, which that matrix must satisfy. Normally, if you apply some particular model, microscopic model, to calculate this phi, you have these conditions satisfied automatically. And we will consider actually one such model later on. So these are conditions which are general for any system. If you have a system which possesses periodic symmetry, like crystals, then you have additional conditions. In order to describe a crystal, we need to describe a number, we need to introduce some other notations. Before, we just used capital A to designate an atom. However, if you have a crystal, you have unit cells, and atoms within the unit cell, each unit cell, are periodically repeated indefinitely in all three directions, or maybe two directions if you have a film or surface, two-dimensional system. So in order to specify an atom in that infinite crystal, you need to specify the unit cell, and then you have to specify the atom within that unit cell, one or the other, and the Cartesian coordinate. In other words, this index A, which we used, to specify an atom this time, will be given by two indices. One is the lattice translation, the vector, which defines the unit cell, yeah, and the S, the atom within that unit cell, yeah. So we need these two indices instead of this capital A I used before. Now, okay, after deciding this, let's again try to see what are the conditions we need to impose on this force constant matrix in that case. Let us displace just one atom in the unit cell L, atom of type S, in the direction alpha. Okay, that means that all other displacements are all equal to 0. In that case, from all these terms, we will be left just with this one. All right? There will be no other terms. Okay, the energy will change because we shifted an atom. But let's ask ourselves a question: whether that energy would depend on that capital L. Because capital L would designate the unit cell in which our atom was shifted. Would it depend on that cell? Or maybe if I take another atom from the nearest unit cell and shift that atom instead, the energy would be different. Of course not, right? The energy would be the same. It should not depend on the particular cell. But here, what we have, if we displace just one atom, we have a diagonal term left for the force constant matrix. And that means that this diagonal term should not depend on the L. And that means that this diagonal term does not depend on L. And that implies maybe that that force constant matrix would only depend on the difference of these two indices. So my force constant matrix in the general notation depends on this capital A and capital A prime. Now in the new notations, it would be L prime, sorry, write it again. L prime, these are two vectors, S alpha, S prime, alpha prime. So what I'm saying, that this kind of little consideration implies that it will not depend on both L and L prime. It will only depend on their difference. And in order to see this fact, let's now perform another mental exercise in which we will take two atoms in the unit cell L, atom S, in the unit cell, the same unit cell L, but atom S prime. So I wrote here L prime, but just imagine for a second this is the same L, yeah, but a different atom, S prime. In that case, only these two, of course, this would imply that we have at least two atoms in the primitive unit cell, yeah? So if this is the case, and we displace only two atoms, one in direction alpha, another in direction alpha prime, then we will have in this sum only three terms remaining, two diagonal terms and one off-diagonal term with respect to the S indices. And again, we know this diagonal terms would not depend on L. What about this off-diagonal term? Not depend on L, not depend on S. What about the off-diagonal term? Off-diagonal term would still depend on S and S prime. But again, we shifted two atoms in that particular unit cell. All right? But if we shifted two atoms in any other unit cell, the result would still be the same. So again, that quantity should depend only on the difference. Now let's take two atoms in different unit cells and repeat this exercise, and you will see here it will only depend on the difference. So this time we displace one atom in the cell L, another atom in the cell L prime, and the result would be the same as we displace two atoms in the shifted cells, but with the same vector between them. It doesn't really matter because the system is periodic where we have taken these two atoms. You see? So the conclusion out of this rather chaotic discussion is that matrix must only depend on the difference of these two lattice vectors. It will not depend on them both separately. Yeah, and this is only the consequence of the periodic symmetry in the system. It will still depend on both indices S and S prime, and of course alpha and alpha prime, but at least here I can safely put the minus sign, and from this time on that will be just one index rather than two separated with a comma. All right, so now after this intermediate or introductory kind of discussion, let's now turn to solving the vibrational problem in the multidimensional case classically. If we want to do it classically, then what we need to do, we need to start from the Hamiltonian of the whole system, which contains kinetic energy. Here, capital M are atomic masses, PI's are momentum of these atoms, and I determined classically like this: atomic mass times the atomic velocity. And here we have the potential energy term. Yeah, I don't know if you're familiar with the Hamiltonian Lagrangian formalism. At some point I will have to use Lagrangian formalism, but here I just appeal to your knowledge of the Newtonian equations of motion. A Newtonian equation of motion is this one. So the momentum dot is a time derivative, is equal to the force acting on the same degree of freedom k. And that force is determined by a minus derivative of the potential energy with respect to atomic displacement. And we already discussed that this would be equal to that expression, where phi is the force constant matrix. So our equation, now we replace P with that, and we obtain an equation of motion for all degrees of freedom. So this is a second order differential equation for the degree of freedom k, but in that sum in the right hand side we have also all other degrees of freedom. So basically what we arrived at is the system of second order differential equations, all linear. So mathematically this is a kind of a very well formulated problem. We have a second order set of linear differential equations without the first order term, in fact, which we need to solve. And the way to solve it is to rewrite these equations in the matrix form first. So if we introduce a vector column for all these displacements uk, call it u, introduce a square matrix phi, capital Phi, for all these force constant coefficients, and I will introduce also a diagonal matrix M for all the atomic masses. So this, all the notations are just introduced. Then that equation can be written in a very simple fashion like that. So it looks like a very simple differential equation to solve. And in fact, it's not very difficult to solve it. And you can solve it in a general case, even though it's multidimensional. And the way to do it is first to introduce, instead of the displacement vector u, another vector v. Let's call it massless displacements, by introducing this matrix m in the power 1/2 here. So what is that m in the power 1/2? It's the same matrix, diagonal matrix like this one, but you have square roots here along the diagonal. Yeah. If you multiply this two matrix with itself, you would recover m. You can also introduce in the same fashion the matrix m in the power -1/2, which, if multiplied with the matrix +1/2, would give you an identity matrix. Yeah. So these are very simple matrices you can introduce either with a square root of m or 1 over square root of m along the diagonal, power 1/2 or power -1/2. And this is what we will be using. Okay. So once I introduce that new notation, and the idea of that notation is to get rid of this m in front of the second derivative. Yes. So that's our kind of purpose. So once we introduce these notations, we replace u with a v. You obtain this formula first, and then you multiply from the left by m -1/2. Then this m disappears, and m -1/2 will reappear here. So you will get this differential equation where now the unknown vector is v, massless displacement, and instead of the phi, we get this matrix D, which has this form, and this is called dynamical matrix. So it consists of the force constant matrix phi sandwiched from both sides with m -1/2. So basically, elements of this matrix, so D, would have indices I and j, and would have 1 over square root mi mj, and this phi ij. So this is the form of that matrix. Yeah. So it's the same as the force constant matrix phi, but each element has this mass prefactor in front. This matrix is also symmetric, and that is important. Why is this important? Because now, as we were set to solve this set of linear differential equations, we can actually arrive at the eigenvector problem of that matrix, which would guarantee, because it is symmetric, that all its eigenvalues are real. How we shall do this? Look at this equation. In a one-dimensional case, that equation would look like this: v double dot plus dv equal to 0. This is a single harmonic oscillator equation. And the solution of this single harmonic oscillator in time, you would take as something, let me use omega, something like ei omega t, right? For a single harmonic oscillator, where the omega would be this coefficient we had in front. Omega squared would be that coefficient. So if we now generalize this to a multidimensional case, we can imagine that to solve this equation, we can take this trial solution. This y would be a vector, the same dimension as this vector v. This will be a scalar factor, which is time dependent, will be exactly the same as for one-dimensional problem. However, with the frequency, which still needs to be determined. So we have two unknowns here, vector y and the frequency omega. Let's see what will happen if we substitute this trial solution inside. We would hope that the time dependence would completely disappear. And indeed, when we differentiate this vector with respect to time twice for the left-hand side, we have this minus omega square coming out, and that exponential. The same exponential would be in the right-hand side, and they cancel out. So time dependence completely disappeared, which proves that this trial solution actually works. There's another method which proves that ansatz, if you like, that trial solution, and I have it somewhere down there. Maybe we will have time for it today, but for the time being, let's get satisfied with that result. And what have we achieved? So we substitute that solution, trial solution, in here. We obtain this or that, and look at this formula. This D is a symmetrical matrix. This Y is a vector column. Omega square is a constant, again a vector column. This is an eigenvalue, eigenvector problem for the matrix D. So by solving this problem, we get both things we were looking for. We didn't know what the vector Y was. We didn't know what the omega were. And now we can determine them all by solving one single problem. Eigenvector, eigenvalue problem for the matrix D. So omega squares appear as eigenvalues of this matrix, and Y appear as eigenvectors. Okay? So if the matrix D is of the dimension n by n, we'll have n eigenvectors and corresponding to them n omega square values. All right? So we don't get one solution, we have n solutions. And for a crystal, which has an infinite dimension or infinite number of atoms, we have an infinite number of such solutions. Okay, so V is determined as a function of time like this, Y this Y. Once we know V, we can determine U, the actual displacements. Yeah, by solving this equation with respect to U, this is easy. We have this m minus 1/2. And therefore, U will be given by that formula. And if we take just one particular eigenvector Y of that eigenproblem with the corresponding to it eigenvalue square of the eigenvalue omega, we will get this displacements, and these are called normal modes. Yeah. So if we have a molecule, for instance, we will have a finite number of atoms, so finite number of such modes. Then we will get how atoms are displaced in time. We can even visualize that with some software. If a particular normal mode is excited, only that one, not others. Of course, in reality, the full solution would be determined as a linear, would be written as a linear combination of all these normal modes with arbitrary coefficients in front, which are determined by the initial conditions, atomic positions before the oscillation started, and atomic velocities at that point, at time equals 0. So this is a classical vibrational problem. Yeah. So this is how it is classically solved. Oh, actually, I have this here. Yes, I have this solution here. So I'll show you also that solution. So how do we determine these eigenvalues, omega square? We determine them by solving this circular problem. Yeah. So this is the determinant of the matrix, which is D minus omega square E is the identity matrix. So by solving this, we will obtain all these solutions. And because the matrix D is symmetric, it's equal to its transpose, it's real and symmetric, we are guaranteed that omega squares are all real. We can't get imaginary or complex omega squares. They will be all real. Also, we are guaranteed in the following. It can be shown that if the eigenvectors of any symmetric matrix can always be taken as orthogonal. Therefore, if we use lambda to designate different eigenvectors and eigenvalues, then the dot product of two vectors, lambda and lambda prime, would be equal to this Kronecker symbol. In other words, if lambda and lambda prime are the same, you get 1. So there will be, the vector will be normalized to 1. But if lambda and lambda prime are different, then the vector will be, the dot product will be 0. So different eigenvectors of this vibrational problem, different normal mode, would be orthogonal. One can also show another condition, which is if you sum over all eigenvectors and you take eigenvector column and eigenvector row, so this T is transpose, so eigenvector column becomes eigenvector row, then this product would have a dimension of the square matrix of the same dimension as our problem. So if you sum over all these eigenvalues, all eigenvectors, you will get an identity matrix. So that's another condition. And if you are interested why this condition comes about, I'll just mention what you can do. You can create a matrix which is called a model matrix of the dynamical matrix. And this is obtained by putting these all eigenvectors as its columns. Yeah, I don't know if you come across this before when you studied linear algebra, but if you put all eigenvectors of a certain matrix as columns, and these eigenvectors are all orthonormal, and we have them orthonormal, this orthonormality condition. They're orthogonal if they're different, the dot product is 0, and the dot product of the vector with itself is equal to 1 if lambda is equal to lambda prime. Yeah, so they're orthonormal, normalized and orthogonal. So if you create such a matrix, then that matrix would be orthogonal matrix. Yeah, so its -1 would be equal to its transpose. All right, but the orthogonal matrix doesn't only have its columns orthonormal, it has its rows orthonormal as well. So if you now write this U matrix as a selection of vectors along the rows, they would also be orthonormal, and that condition is precisely that. So these two conditions are important because they come in several places. And now, how about time? So I have just time to do this. Let me just check where I am. 7. Okay, I'm actually going very slow. So, okay, so here, what, maybe I'll skip this. Let me skip this. Let me skip this. You will get this slide because there will be slides posted on the web page as slides as well, apart from the video, I suppose. And
yeah, they are already in the website.
They're already on the website, yes.
Yeah.
Okay, so stability. Let's look at the potential energy. Potential energy of our harmonic solid is given by this. This is the force constant matrix. This is a vector column, vector row of the atomic displacement, vector column of atomic displacements. Now, introducing this dynamical matrix instead of the force constant matrix, I have this expression. Yeah. So the dynamical matrix is given like that. So if you go backwards, you will have m in the power +1/2. So we have that. Now, by writing now the dynamical matrix in terms of these eigenvectors and eigenvalues, I can use this formula. This is called spectral theorem. You can easily establish that if you take this d, apply it to some lambda prime, you will have omega lambda prime square y lambda prime because of the orthogonality of the eigenvectors. So this is an equivalent expression for the eigenvalue eigenvector problem. So if I now put this instead of d here, I can rearrange this energy expression into that form, then write the sum of the lambda over all eigenvalues, take omega lambda square out, and have these two expressions here. What are these expressions? Here u is the eigenvector, is the vector of displacement, vector column. Y lambda is our eigenvector of the dynamical matrix, but we take the transpose of it, so it's a vector row. So we have a vector row multiplied by a vector column. It's a dot product. It is a number. Yeah. So that number bears this index lambda because of the lambda here. So these are two numbers, and this number taken transpose is the same number. So we basically have just that number squared. So in terms of these eigenmodes or normal modes, little y lambda, my potential energy becomes just a sum of squares with respect to displacement. So this y lambda, these are normal mode, these are displacements, but these are collective displacements because they contain a sum. This dot product is basically a sum with the coefficient being eigenvectors of all atomic displacements. U is a vector, right? So this y lambda corresponds to displacing all atoms in a very specific way, which is characterized by this eigenvector. So these are collective displacements. So in terms of collective displacements, the total energy becomes just a sum of independent collective displacements, which are this y lambda with a prefactor given by omega squared. And we know, as I said before, that these omega squares are always real. And in fact, the eigenvectors can always be chosen real as well, because the dynamical matrix is real. So we have a sum of these square terms. What are the implications of this? All right, let's assume that all omega squares are positive. We know they're real, but they could be positive or negative or zero. Yes? Okay, so suppose they're all real, or positive. That means that these coefficients are positive. And that means that if we take any values y lambda, so any displacement of atoms from equilibrium, y lambda equal to 0 corresponds to equilibrium, exactly the position of the minimum. Yes? Because these are this linear combination of displacements. So if we displace atoms in any way, we definitely have an increase of the potential energy. Yeah. So if all omegas are positive, that potential energy form would be of that shape, with the point when all lambdas are equal to 0 corresponding to its minimum. Yeah. Okay. So this means we have a stable minimum of the system. We don't know whether this minimum is global minimum or metastable minimum, but at least we know it is stable minimum, because this quadratic form, which we had before, this one, is positively defined. Yeah, and the proof of that is that all eigenvalues are positive. If, however, at least one eigenvalue is negative, what that means? That means that we have a bunch of positive terms, but we also have a term like this one, minus that frequency module squared, yeah, but with a minus sign, which means that if I displace atom in that particular way, corresponding to this lambda, this normal mode, the energy actually goes not up but down. Yeah, so if I have a single frequency which such that omega square is negative, and therefore the frequency itself is imaginary, then there exists a direction in space such that if I displace atoms in this direction, the energy actually goes down. If I displace atoms in all other directions, the energy goes up. So we have a situation which is called a saddle. Yeah, from that point where all the derivatives, first order derivatives are 0, because this was our starting point. The linear term in potential energy expansion is 0, which means that the forces acting on atoms at that point are 0. But we discovered that in terms of the second order derivatives, the situation is more complex. So the dynamical matrix has a negative eigenvalue, and therefore in some of the directions the energy goes down. So this is an unstable stationary point, and this is a saddle because in some directions the energy goes down, in some others it goes up. It is a saddle. And if you look at the displacements as they depend on time, they depend on time via this exponential factor. So if the omega is imaginary, you can imagine that there is a component in the displacement which goes indefinitely up with time. So the system becomes unstable and disintegrates. Another situation could be that all omega squares, the eigenvalues of the dynamical matrix, are positive, but some of them are very small, which means that the potential energy surface in that direction very, very flat, which is called a soft mode, which means that it is expected that the barrier to escape from that minimum is small, and therefore the rate of transition out of that minimum would be significant. Do we want to have a few minutes break? It's okay?
Yeah, it's okay for me.
It's okay. I'm on slide 9. All right, I'm going. Okay, good. Okay, a few minutes break, guys. Yeah?
Okay.
Okay. Are we ready to continue?
I am at least.
Yeah. I only see your face, so I'm always talking to you in some sense.
Okay.
Showing their faces. So, guys, if you like to show your faces, maybe you would like to ask some questions. I was going rather quickly through all this. Are there any questions so far? No. If you have any questions, you can also email me and ask questions. Okay, so let's move on. I don't know why this appears. Why is this? Can you move it? Oh, okay. No, it doesn't. Okay. All right. So these are kind of general things we just considered. And I have prepared also a few nice examples of how to find, how to solve the classical vibrational problem for both finite and crystalline systems. Oh, I have new face appearing. Hello. Right. Okay, so let's look at the finite systems first. So finite systems must be translationally and rotationally invariant. As we discussed before, this dynamical matrix must satisfy certain conditions. This can also be imposed by force by looking at this invariance. So if we would like a system be translationally invariant, we can impose a condition that the momentum of the system for any displacements is 0. And that means, because we have time derivative here, that that quantity must be constant. And we can take a value of 0 for that constant. Yeah. So the linear combination of atomic displacements time mass must be equal to 0. And you can easily recognize here that that actually is nothing but a center of mass being taken as the 0 of the coordinate system, or the center of the coordinate system, the center of mass, which looks reasonable. In terms of rotational invariance, one can require that the angular momentum is 0. Yeah, angular momentum of the system is 0. The angular momentum contains these actual positions of atoms and their actual velocities. Actual positions are given by positions at equilibrium, R naught, yeah, plus a displacement. And for small displacement, the product of these two terms, that term, of course, because we have a sum of two terms, this expression would be given as a sum of two terms. And we can neglect the term quadratic in atomic displacement and only leave the term which is linear. So we neglect this then and arrive at that expression here. And again, we have time derivative of that UA. And therefore, this can be written as a time derivative of that expression here. And again, we can claim that this, which is equal to 0. And then we can claim that this expression must be equal to a constant, which we choose as 0. What we have arrived at are the conditions. So here, there are 3 conditions in the 3-dimensional system for the atomic displacement, which corresponds to translational invariance. And these also are 3 linear conditions for atomic displacements, which corresponds to rotational invariance. What does it mean? It means that if you have a system which contains n atoms, we have 3n degrees of freedom, right? But because of the translational and rotational invariance, we actually have 6 degrees of freedom to be eliminated, because they correspond to translation of the whole system or rotation of the whole system. So the actual number of degrees of freedom is 3n minus 6 for a 3-dimensional system. Okay. Of course, if the system is not 3-dimensional, like a water molecule is 2-dimensional, or a linear molecule is 1-dimensional, that number of degrees of freedom you have to eliminate is smaller. Okay, so let's consider as an example this linear molecule. So I will show you how this actually works. It's a simple molecule with two atoms identical here or on both sides and another atom in the center. And we can write the potential energy of that system in that form. Atoms are numbered 1, 2, 3. So we have a harmonic spring, if you like, here and another harmonic spring here. So the sum of the potential energies is trivial. We just subtract the displacements of atoms. Yes? And because the system is 1-dimensional, rotational invariance here is meaningless. We only use translational invariance and only along the x direction. So we assume that atoms oscillate only along the 1 dimension here. So out of these 3 conditions, we choose only one. These conditions are not of relevance to us at all. And therefore, we write the center of mass condition like that, which means that we can eliminate 1 coordinate. So here, 3 atoms, we have 3 coordinates, x1, x2, x3. We can eliminate 1. So the system would become effectively 2-dimensional now, yes? So we can eliminate x2, for instance, and then x2 will be defined y x1 plus x3. Now we can introduce 2 new coordinates, call them q, as a sum of 1 and 3 and the difference of 1 and 3. And because x2 is proportional to the x1 plus x3, which is this qa, we are able actually to express each of the coordinates x1 and 2, x3 via just two coordinates, QA and QB, in that fashion. Okay, that's a very simple statement. Now, the idea is to write the kinetic and potential energy of our molecule via only these new coordinates. If we can do this, then we would be able to solve the vibrational problem in terms of these new coordinates. These new coordinates are not yet normal coordinates. They might be, but if we guessed correctly, but it's just another choice to simplify the energy. So if we now look at the potential energy, which is given here, and instead of this axis, we replace them using that formula, we shall arrive at that expression for that expression for the potential energy, this one. You see, it's a sum of two independent terms. Now we can also write the kinetic energy in the same fashion, but kinetic energy would contain kinetic energy of each atom, and again we substitute them in here, and again the kinetic energy splits up into two terms, one depending on QA and another on QB. So we see that the total Hamiltonian of our system is actually equal to the sum of two independent Hamiltonians for the degree of freedom, for the generalized coordinate QA and another for the QB. And each of these Hamiltonians is just a Hamiltonian of a single harmonic oscillator. Here we have this prefactor, which is m/2, with the m being some effective mass. And this is the kinetic energy, kq²/2, with the sum k, which is effective spring constant. All right, not that one k, another k. So you see, we can straight away write what the frequencies for these two cases are, and they're given by this formula. So see, we were able to solve this linear problem employing this center of mass condition. And now we can have a look what these two normal modes would be for these two frequencies. For that, what I need to do is to look at that formula. So if I excite only QA mode, that means the QB mode is 0. So this is 0, this is 0. Then we have x1 and x3 being the same. You see, they move synchronously together, but x2 moves in the opposite direction, minus QA. And if mass m is larger than 2 masses m, that prefactor is small, and therefore that displacement would be small, otherwise it would be large. So the first and the third atom move to the right, the middle atom moves to the left, either by a larger or smaller amount, okay, depending on the masses. If instead I excite QB mode, so QA mode is 0, then x2 is not moving at all, and x1 and x3 move in the opposite directions. So we have this normal mode. Okay. Now let's consider a miles more interesting problem, which is the water molecule. In the case of a water molecule, it's non-linear anymore, but it's a planar molecule. So in this case, we have 3 atoms. In a plane, we have 6 degrees of freedom. Yes, and this time, for this two-dimensional problem, we have 2 translationally invariant conditions and 1 rotationally invariant, because we can rotate this molecule around the axis perpendicular to the plane of the slide, and that rotation here is to be considered. You see, so we have 3 conditions. So 6 degrees of freedom, 3 atoms, 2 dimensions, 6, and we have to eliminate 3 coordinates by 3 conditions coming from translations, 2 conditions, and rotations. Rotations, it's quite easy to implement actually. If you look at the rotations, this is that we have to sum over all atoms and take the vector product over atomic position at equilibrium and its displacement. Here, atomic positions at equilibrium for the oxygen with my choice of the coordinate system is 0. So the oxygen contribution is 0. Concerning the 2 hydrogens, one hydrogen is at a position L sine L cos, alpha is this, L is that distance, and another minus L sine L cos, yes? And if you do this vector product, you will find that only the Z component of the vector product is non-zero. And that Z component will give rise to this equation. So now we have three equations, this, and this, which would allow us to eliminate three variables. We follow exactly the same procedure as before for the linear molecule. We introduce three new generalized coordinates Q, QA, S1, and S2, like shown here. And using those conditions and these three additional definitions, we can actually define or express all the coordinates, all 6 coordinates, x1, x2, y1, y2, x3, y3, via these Q coordinates only. And these are shown here. Okay, so now we have access to everything. We have only 3 independent coordinates Q, and we have all 6 coordinates expressed by them. So what we need to do now is to write potential energy and kinetic energy of my molecule, right? So the potential energy, we shall assume, is given by this. So what is this? This is the change of the length here. It's harmonic with some spin constant K1, and change of the length here. Plus, we have a term associated with the change of this angle. So we need 2 things now. We need, first of all, a formula for the change of the length, change due to the fact that this atom displaced and this atom somehow displaced. And we need a formula for the angle here when these 3 atoms are arbitrarily displaced. And we need to remain within the harmonic picture. So we need to retain only terms such that that we will remain, the total potential energy would be still harmonic, quadratic in displacements. And because the potential energy is quadratic in this change of the alpha or change of the length, our expressions for the change of the length and change of the alpha should be linear in atomic displacements. Then we will remain within the harmonic picture. Is it clear? Because the energy already quadratic, so this, each of those must be linear. Of course, if you derive an exact expression for them, they won't be linear. They will contain square roots because you have to write the length. But in order to keep only linear terms, you arrive for the length into this formula, and for the alpha into this formula. And this, you see, they're all linear. And now if we take these rather bulky expressions in the expression for the potential energy, and we'll make some very simple but rather long transformations, we will find that the potential energy has QA term completely independent. It's quadratic, you see, for us, for the harmonic oscillator, with a positive prefactor here, good. But QS1 and QS2, they have 3 terms. So there is a quadratic term for one and the other. There's also a hybrid term, which has both of them together. For the kinetic energy, we have to perform the same calculation as before, but this time we have the time derivatives of them. And if we again replace these coordinates via the Q coordinates, and do all the algebra required here, which is a bit long, but it's essentially very simple. Again, you arrive at 3 independent kinetic energy terms. So QA is completely independent in the kinetic energy and the potential energy. And therefore, with QA, we immediately can identify a particular vibration. And here, the vibrational frequency is given by that expression. Okay. And if you now set 2 other displacements to 0, S1 and S2, and look at the coordinates, how the coordinates actually change when this particular QI displacement is only excited, then you will find that atom 1 moves like here, atom 2 moves like there, and the oxygen moves in that direction. So this is the equations you obtain. So you can see how atoms move when this particular normal mode is excited. And when this atom moves in that fashion, the center of mass remains the same and the molecule doesn't rotate as a whole, because we impose those conditions from the very beginning. Concerning QS1 and QS2, we have now potential energy containing this term. So the Hamiltonian with respect to these two is not the sum of the two Hamiltonians. You have to solve this two-dimensional vibrational problem. And therefore, you have to solve this set of two vibrational equations, which can be solved exactly in the same way as I explained before. If you remember this classical problem we discussed, where is this? Here, yeah? Yeah, but this time we have a two-dimensional problem only. Essentially, the solution would be some of the solutions associated with the eigenvectors of the dynamical matrix. And here, the dynamical matrix, this effective dynamical matrix here, will be served by this matrix, which comes from the kinetic and kinetic and potential energy, essentially. And if you do this, you would derive from the secular problem to this rather bulky looking equation for the omegas, but it's a quadratic equation with respect to omega square. It will have two positive solutions. You can determine these omegas for one and the other, and determine the eigenvectors. And if you, when you determine eigenvectors, you will find that these two displacements, QS1 and QS2, are proportional to each other in each of these eigenvectors you will find. To cut the story short, I'll just show you what actually happens. If, say, first of all, QA, the first displacement will be 0. We excite only one mode. And then we excite only one mode, QA is 0. These displacements we have, actual physical displacements of our atoms, are expressed by this generalized displacement in this way. And because in normal modes, QS1 is proportional to QS2, but with different proportionality constant because of different solutions, you will arrive at two eigenmodes. In one, hydrogen atoms move like that, and oxygen doesn't move. And in another, it's kind of a breathing mode. Hydrogens move like that, and the oxygen moves like that, down, up and down. Yeah. So these are solutions you will get for the water molecule. Now, performing an ab initio calculation on the water molecule by displacing atoms, you can actually map up its potential energy surface as the function of these two distances and the angle between them, and you can arrive at something like that. So this is a working model, a classical model for the potential energy of the water molecule in terms of these parameters we just introduced. And the constants are given here. You can even add more terms to the model, make it better, and then solve it in exactly the same way. The calculation would be much bulkier, but in principle, you can do this. Of course, you can do it numerically from the very beginning, but it's kind of nice that this analysis allows you to do it analytically. How are we doing in time? Oh, half an hour left. I think I'm talking too much. In the case of a crystal now, which is characterized by periodic symmetry, it's still the same eigenvector, eigenvalue problem, but this time, this product of the matrix D and the vector column Y would be this triple sum over all lattice translations, over all atoms within each cell, and all the Cartesian components. So this system of equations is an infinite eigenvalue eigenvector problem. It's difficult to solve. However, we can use the fact that the dynamical matrix is actually contains the difference of the lattice translations here. You see L here, L prime here, we sum over L prime. So L is still present in the left-hand side. All right. And because of that, one can easily show that I probably don't have time to go into details here, but one can easily show that by using the Fourier transform, that infinite problem is equivalent to a set of many finite problems like this, where dk is a sum, lattice sum of my matrices DL. Yes, so now this L minus L prime, I call just one L, and a sum over all these L vectors, multiplied by this plane wave kind of phase factor. And of course, when I calculate this sum, the obtained matrix would not contain L index anymore. It would only contain indices S alpha left. So this matrix dk is a finite matrix, and the size of that matrix is equal to the number of degrees of freedom we have in a single unit cell. The number of S indices times 3 because of the alpha indices. So this is a finite matrix, but it is specified by, for a particular K vector. K vector is a vector in the first Brillouin zone of the reciprocal space of my crystal. I just hope you're familiar with the concept of the reciprocal space and K points. So we define this matrix, and therefore we determine eigenvectors and eigenvalues of that matrix instead of the original matrix, which has an infinite size. Now we determine this for a finite size matrix, and this yk is a finite size eigenvector of that matrix, and that is related to the infinite size vector yl. Why this expression where we sum over all L? Yeah. And basically that means that by determining all solutions for all possible values of K, we will be able to describe the oscillations, vibrations of that crystal. Of course, we shouldn't fool ourselves. We initially had an infinite size problem, so we should still end up with an infinite size problem. But you see, the difference is fundamental. Here we have an infinite number of finite sized problems to solve. So we can actually solve this problem for any K vector in the Brillouin zone we like. The number of K vectors is infinite in the Brillouin zone, or very large. Yeah, but still, if we assume the dependence of the frequencies on the K points is smooth, we don't need to solve it for every single K point in the Brillouin zone, and we can limit ourselves with a nice selection of these K points in the Brillouin zone, and then interpolate our solutions from one to the other. So that means we basically solve the problem. This infinite sized problem can actually be solved by using this, by going into the Fourier space from L vectors to K vectors in the reciprocal space. Yeah, and this allows us to determine solutions. If we would want to do better, we take more K points, even more K points, but basically the dependence of the eigenvectors and eigenvalues on the K points is smooth, so we will be able to determine them out of a finite number, maybe large, of K points, but maybe not that large, yeah, depending on the system. Two simple examples here as well: one-dimensional chain of identical atoms, monoatomic chain, and diatomic chain, again one-dimensional of two different atoms. These are standard examples from any solid-state course, and what you do here, you simply do exactly the same calculation as we did for, say, a water molecule or a one-dimensional molecule. We set up the potential energy, kinetic energy. So this is the potential energy, this is the kinetic energy, but we have to sum over all atoms. This is an infinite chain. And then we set up Newtonian equations of motion. Here I did it while Lagrangian, but it's basically the same thing. We can always calculate the forces. Maybe this is what you've seen in your courses or on the solid state, and you arrive at a set of infinite set of differential equations like that one. Yeah, and it is solved by using this trial solution. So we first of all time dependence make as a e to the I omega t, but also these amplitudes we make as depending on the atomic position in that exponential form. This corresponds to the general statement how the solutions should depend on the vector L. And here the vector L is one-dimensional vector. It's just NA. N is the atomic cell, and A is the distance between atoms. Yeah. And if you do this, substitute in this equation, you will obtain a very simple equation for the constant A and for the constant K. Yeah. And you will find that omega square and omega depends, so A cancels out, and omega square depends on the K in that very simple fashion. So by specifying different K, we get different modes, vibrational modes. And the displacement is like that. So you see, omega gives the vibrational, how the vibration changes in time at a particular point. And here we see what are the amplitudes at different points on the lattice. And the larger K, the smaller like wavelength of this wave would be. The smaller K, the larger wavelength there would be. So K equals 0. In particular, we'll have all displacements at the same across the whole chain. Yeah. In the limit of this A, the distance between atoms going to 0, we will get an elastic solid. We will get elastic waves. Solutions like this. K would change only within the first breathing zone. If you go beyond the first breathing zone, the same solutions are obtained. So that K is an arbitrary parameter, but it changes only within these limits. If you go beyond these limits, as I say, because of that exponential, nothing will change. So it's only sufficient to keep K within this first breathing zone of the one-dimensional crystal. If you have two atoms in the unit cell, you perform exactly the same analysis, but this time you will have two branches, not just one. So there will be two solutions for the omega. One is called optical, another is called acoustic. Here we'll have only acoustic solutions. If you K equals 0, you have omega square equals 0 as well. So your solution would look like this. But in the case of the two-dimensional, diatomic system, you have two solutions. One, which goes to 0 at small k, at 0K, and omega changes linearly with the K at small k. Another at K0 has a finite omega. This is the optical mode. And in the optical mode at small k, atoms oscillate in opposite directions. For the acoustic mode, atoms oscillate with the same phase, which is what you would expect from an elastic wave. When you have an elastic wave, the whole crystal displaces in phase. Yeah. But in the optical mode, atoms oscillate with opposite phase, and that's why if atoms are differently charged, you would have a strong interaction with electromagnetic waves. Yeah, that's why it's called optical. But again, K is still changing within the first breathing zone. Maybe I'll skip this as well. How can we determine vibrations using an ab initio calculation? So I will consider with you two methods. Again, rather briefly, but I will try to give you an idea. The first method is entirely numerical. Actually, both methods are numerical, but the second one is less numerical than the first one. So let's start from the simple one, which is called frozen formulas method. The idea is as follows. Suppose we have a molecule like this, or it could be a part of a unit cell of a crystal. So this thing is periodically repeated, okay? And let me displace just one atom. All other atoms are in the equilibrium positions. If I displace just this one atom, the force on any other atom, B, direction beta, would be given by this. Yeah, so the force is given by that linear expansion with the full force constant measures, but because only one displacement is non-zero, we're left with a single term here in that sum. All right, so we know the displacement. And from the ab initio calculation, we would know the forces acting on atoms if we do this displacement, perform this displacement on that single atom. dividing one on the other, we will get the component of F. You see, it's very simple. You take your cell, you displace one atom, you calculate the total energy and the forces. You don't relax anything. It's just single point calculation. And you know the forces on all atoms when just one atom is displaced. So by dividing all these forces on that particular atom, I get a row. Is it a row? 1, 1, 1. I have a column of the force constant matrix, this A alpha column. I can do a little bit a better calculation. Instead of displacing just in one direction, I can displace in another direction as well by the same amount. Then I can perform the same calculation and take the average of the two. And this way, I would arrive at that formula for the elements of the column, A alpha column of the force constant matrix. Then I take another atom, yet another atom, and another atom. I will get all the columns of the force constant matrix, the force constant matrix calculated. Of course, there's a little problem here, because when displacing atom 1, you have forces on atom 2, and therefore you have element 2, 1 of the force constant matrix. But displacing in atom 2, you have the force on atom 1, and you have the same element of the force constant matrix 2, 1, because the matrix is symmetrical. And of course, in performing a numerical calculation like this one, you will have these two calculations given different values of this of diagonal element 1, 2, and 2, 1. So you may symmetrize the matrix to make it symmetric by force, by taking the average of these two calculations. You can use the symmetry, and then the number of calculations would be reduced. So this was for a molecule. This is what you could do for a molecule, for instance. In the case of a crystal, the situation is a little bit more complex, because in the case of a crystal, we would like to determine this vibrational frequencies and normal modes for different K points. Remember how the displacement for a given K point, eigenvector, or the K point, related to all displacements at different lattice sites. If my displacements at different lattice sites are the same, so this Y of L doesn't depend on the L, I can take this out of the sum, and that thing here would simply give me a canonical symbol for K equals 0. So if I deal with a primitive unit cell, this one, and displace all atoms, therefore, in all cells in the same function, keeping the periodic boundary conditions, I have access only to K equals 0 phonons. If I would like to have access to other phonons at other K points, I have to increase my unit cell. I have to enlarge my unit cell. In that case, I have access to phonons at different K points as well. Let's look at this in a bit more detail. So if I have a primitive unit cell, my Brillouin zone is like this. If I take 4 times Brillouin zone in the direct lattice cell larger, my Brillouin zone would be 4 times smaller. Yeah. So different points of the original Brillouin zone now will be related by the reciprocal lattice translations of the reduced Brillouin zone. Lattice translation overall, in that case, can be written as the lattice translations associated with this large extended cell, plus small translations, which are here within that large cell. Of course, if I enlarge my cell 4 times, I will have 4 such small translations: 0, this one, and this one. Okay. Right. So when I now write an expression for the dynamical matrix at the given K point K of the original Brillouin zone, I will have to calculate that sum, which contains the sum over all translations of my crystal. And here will be this exponential phase factor. Okay, that translation can be written as translation over the large translations associated with the large cell, and translations due to internal translations. So in this case, there will be this one, right? And 0. And I can then rewrite this expression in that form by taking these capital N translations inside this factor and call it little f. All right, just this still exact, no approximations so far. Now let's consider k points in the original brilliant zone, which satisfy this condition. In other words, that exponential for them, for any capital N, would be equal to 1. It's easy to see that these k points must be a linear combination of the reciprocal lattice vectors associated with the extended direct cell. Yeah. So with this lattice vectors, if I take a linear combination of these B vectors, so B, capital B, are these ones. These are small b's. Yeah. So as I said, capital B's are smaller. The product of the two, capital B and capital A, where A are extended translations of my extended cell, would give me 2 pi and the chronicle symbol. And therefore, that product, K by N, would give me an integer, 2 pi times an integer. And therefore, this exponential function would be 0. So, for instance, K equals 0 would be such a point. But that point, and that point would also be such points, because they're obtained by single translation associated with the reduced brilliant zone. So even though K equals 0 obviously satisfies this equation, other 3 K points, this one, this one, this one, which are legit
Professor, you're on mute.
You must have lost me at some point. Yes?
Yeah.
Did you lose me? Did I explain this bit? Did I manage to explain that bit? So when I was talking about 4K points in the original zone, did you hear this part? Hello?
You were saying something about the trivial solution about 0, but
all right, okay. So did you get the point that if K vectors are a linear combination of the reciprocal lattice vectors associated with the reduced brilliant zone? Yeah, so if these K are like this, then that expression is satisfied for any large translations. So this is that line of reasoning here. Yeah, because this K would be a linear combination of the big B, reciprocal lattice vectors. Capital N is a linear combination of the large A, direct lattice vectors, or the extended lattice. And then we do the dot product. This would give you 2 pi. and all others are integer numbers. So even though for k equals 0, that equation is obviously satisfied, it is also satisfied for these 3 points, which are obtained by adding these capital B's. So in fact, that expression for any capital N is satisfied for 4 k points in my example here. This one, this one, this one, and this one. And these are all legitimate k points of the original Brillouin zone. So for these k points, and only for those k points, that exponential prefactor is equal to 1. And that expression here, this f, little f, is just the sum of the force constant matrix over the whole extended lattice. Now let's do the following exercise. Let's shift just one atom within this extended cell, the atom which belongs to the 0 primitive cell, just this atom. So that atom would bear this index n, little n, 0. In that case, we can calculate forces on all atoms of our full extended cell using DFT. Okay, and that force would still be given by that expression without any exponential prefactor, because this is what it is. So by knowing this displacement, because we move the atom manually, and knowing the forces on all atoms of my extended cell, I can work out this sum. But this sum is exactly what is this f little is, if that k points are such that satisfy that the condition that this exponential is equal to 1. Therefore, for those k points, and only for those k points, I have access via this formula to D. All right? This is exact, no approximations whatsoever. Yeah. Apart from numerically calculating these displacements, of course, you do the displacements, and of course, the energy, the force is not only this. When you do displacement, there will be other terms as well. But if the displacements are small, then and if you do the calculation in the positive direction and negative direction, you move away these other non-zero terms to higher and higher orders of U, and therefore for small displacements, these terms would give a small contribution, a negligible contribution. Right. So this method is exact, and it allows us to do the calculation for different k points and obtain the phonons for phonon frequencies and eigenvectors. How in practice you can perform these calculations? You have to choose a unit cell, extend it. So if you use a primitive unit cell, you obtain this way only vibrations at k equals 0. Now, you take an extended unit cell, say 2 by 2 by 2 extended, and then will be a time extension. Then you can determine which k points actually can be reproduced by that particular extension. So basically what you need to do, you need to solve this equation with respect to the k points. This can be done. Yeah, so there is a way to do it, and you can determine these 8 k points for which that method actually works. And then you have to shift atoms in a particular way to obtain the forces, and then from the forces you can obtain the force constant. The force constant is this little f, and by performing this sum, you will obtain the dynamical matrix. All right. One can do a little bit better than that, and one can actually determine which particular atoms and in which fashion you have to move to excite just one vibration associated with that k point only. Yeah, this way you can simplify your calculation. If you want to, that basically means that out of 8 k points which we have, in fact, several of them will be associated with the k points which are rotated with respect to each other. You don't need to do calculation here because they would correspond to, if there's a symmetry in the crystal, they would correspond to the same omegas. Yeah, the same vibrational frequencies. You can then take a unit cells of different shape and size. They will give you different K points. You can ignore K points which you already have, and only do displacements to determine K points which are new to this particular unit cell. And this can be done actually by taking very small extensions. You don't need to take 10 by 10 by 10 extension to have great number of K points and then perform the calculation. You can get away with taking small extensions like 2, 1, 1, 1, 2, 1, or 2, 2, 1, 2, 2, 2, maybe 3, 1, 1, even non-symmetric extensions. And this will give you all access to various K points. And the advantage of that is that the smaller the system you consider, the faster the calculation would be, more efficient. So instead of taking one big calculation on a very large cell, which contains many K points, is much better because of non-linearity of time with the size of the system. It's better to take many systems, each smaller. And there's a code called Tether, my code, which actually does all this. Yeah. You can interpolate to other K points in a simple fashion. I just wanted to, if I have, maybe I'll leave it to the next time, that density functional perturbation theory. It's something I wanted to consider as well with you as an alternative to this method. No, probably we'll leave it to the next session next week. The only thing I will mention here is that the problem with this method, apart from the fact that you have to displace atoms by hand and then perform a DFT calculation, and then the forces on atoms would come not only linearly, but there will be higher powers of the displacement in the expression for the force, which we neglect, and therefore this makes the calculation approximate. We have a problem of symmetry. If you displace one atom, the force is on another atom. And if you do the opposite, displace this atom and calculate the force on that atom, you will get access to the same elements of the dynamic of the force constant matrix, which will not be the same because of the mentioned higher order terms and numerics which is required to calculate the forces with DFT. That method requires some care, but there's also another point. If you would like to have small K points close to the gamma point, you have to have a very large extensions, and there is some barrier for you to do because you can't take very large cells. The calculation becomes prohibitively expensive. So for small K points, this method is actually useless. But you can determine still the dynamical matrix and therefore vibrational frequencies for the K points which are on the surface of the Brillouin zone, maybe in the middle of the Brillouin zone. You can take some specific direction in the Brillouin zone and determine vibrations along that direction, not very close to the gamma point. Yes. So if you want to perform calculations by sampling the whole Brillouin zone nicely on the grid, then another method, which is density functional perturbation theory, should be used, which we will consider next time. It operates with the primitive cell from the very beginning, and it allows you to calculate vibrational frequencies and vibrational eigenvectors for any K point, no matter where it is in the Brillouin zone, very close to the gamma or far away.